All right, today I'm going to go over some of the two-dimensional motion practice problems with you. So far you've been doing things kind of like in a linear motion where they're either going back and forth or up and down, but now we're going like left to right and up and down at the same time. So our first question here is about a ball being kicked horizontally off of a cliff, and then later on we're going to have things that are going to be moving at an angle. So those are two different types of problems, but they both involve horizontal and vertical motion with our kinematic equations. So we need to know how to set those up. Now for sure the easier ones are horizontal motion, and so that's what we're going to start off with and kind of just get an idea of what is going on. I always suggest drawing a picture when we're doing things, and in this case we have a ball being kicked horizontally at 8 meters per second off an 80-meter high cliff. And they want to know how far from the base of the cliff will it be when it strikes the ground. So this thing's going to go off like this, and we want to know what our delta x is. That's our question. So anytime we do a kinematic equation, we need to list out what is our given and what is our unknown. But in this case, we have givens and unknowns in both the vertical and the horizontal direction. So I just say, hey, these are going to be my x direction things. And underneath here, I'm going to list my y direction. So I'm going to start with my given. So horizontally, we know that this thing, I'm going to call it VIX, is 8 meters per second. What do I mean by VIX? V for velocity, I for initial, and x is going to be the x direction. So I know that this thing is traveling at 8 meters per second. Now, throughout its trip, no matter where it is in its motion, the velocity horizontally stays the same. And the reason why is we're ignoring air resistance and there's nothing else pushing it or pulling it left or right. So the acceleration, the change in velocity in the x direction is 0 meters per second squared. It stays the same. And so we could even say that our final velocity, VF, in the x direction is also 8 meters per second. So all of those stay the same. This is going to be my given in the x direction. Let's write it like this, given. Now, unknown is the delta x right here, so that's unknown. I don't know how far left it's going, don't know. Or, sorry, how far right it's going. That doesn't, that's unknown. And I also don't know how long it's in the air. So this is like our find. So there's my two unknowns that way. Now the y direction is going to help us figure out some of those things. So if you want, pause the video, see if you can figure out what's going on in the y direction. I'll give you a moment to pause it. All right, I take it that you gave that a try. So let's talk about the initial velocity in the y direction. In this case, how fast is it moving up and down when it's kicked off here? Well, this is just getting kicked off not at an angle, but at 0 degrees, right? So vertically, there were no forces put on it in the beginning. So it's 0 meters per second. Now, it will start to fall faster and faster as we go further and further down because gravity is accelerating it. How fast is gravity accelerating it? Well, the acceleration in the y direction is going to be 9.81 meters per second squared. Now, I let that be positive, so in this case, it's kind of important to note that, hey, I'm letting down be positive and up be negative as far as our directions go. Now, you can let down be negative if you want, but gravity better be negative, and our displacement here, our delta y that we're going to be talking about, should be negative as well if you're letting down be negative. But I'm letting down be positive, so my delta y here is going to be negative 80 meters. These are my givens, right? I know that from the problem. What is unknown is I don't know the final velocity in the y direction. And honestly, I don't care about the final velocity in the y direction. That's the moment right before it hits the ground, by the way. A lot of students want to say that the final velocity in the y direction is 0, but we're counting like right here, right before it hits the ground. Because the higher up we are, the faster it's going to be in that moment right before it hits the ground. And I also want to know what is delta t. So anytime we're doing two-dimensional motion problems, delta x and delta y, velocity in the x, velocity in the y, acceleration in the x, acceleration in the y. A lot of times all these things are different, except for one thing. The one thing they have in common, if we're breaking the ball up into horizontal and vertical motion, is delta t. This must be the same because the ball is a physical object and can be in the air only for a certain amount of time in the y and the x direction. It has to be the same amount. Okay, so a lot of times this is our connecting variable to connect these two. So I've got enough in the y direction to figure out delta t. In fact, we're treating it just like if this ball was right here and just dropped straight down. Guess what? It's in the air for the same amount of time as if it's dropped straight down versus being kicked horizontally, because the only thing affecting it vertically here is gravity. So with this, I'm going to use my equation that delta y, our displacement in the y direction, equals our initial velocity in the y direction times time plus 1/2 gt squared. I say g here, but remember that's the acceleration due to gravity. That's the same thing as acceleration in the y direction. So the next thing I'm going to do is start substituting things in. I've got, oh, wait a minute. We want it delta y here to be positive because we're letting down be positive. So it's going to be positive 80 meters equals 0. That's my velocity in the y direction, initial velocity in the y direction, plus 1/2 times 9.81 times delta t squared. 1/2 times 9.81 is 4.905. Still got time squared. 0 times t is just 0. That's nice. And we still have 80 meters there. So let's divide both sides by 4.905. See if I can get this in a nice spot where you can see it. Maybe not, there's a glare. But I'll go ahead and say 80 divided by 4.905 equals 16.3. And then square root that. So to square root it, I just hit second, square root right there, and then second again. And the answer, if you got one of these calculators, you can say, hey, enter answer right there. That's a nice, easy way. You could type it out, and I get 4.04. That is my delta t. Double check your math, double check my math. Oh, guess what I forgot to put in here? You need something in here. You need units, right? It's not meters, it's not miles per hour. It's 4.04 seconds. This is my delta t that goes in for my x direction. Now I want to know how far to the left it goes. We know that horizontally, it's always traveling horizontally at 8 meters per second all the way through. So if I know how fast I'm going, 8 meters per second, and I know how long I'm going that fast, which is 4.04 seconds, I can multiply the two and get how far I go. So 8 times this, I'm actually going to leave that in the calculator like it is and hit times 8, and I get 32.3. So 32.3 meters. That is my delta x and my answer to number 1. All right, there's your answer. So that was being launched horizontally. What did horizontal launch do for me? Well, I know that the initial velocity in the x direction stays the same throughout, and then I just treat it like I'm dropping it from that height to figure out time, multiply it by that horizontal velocity, and that gives me my total distance traveled. Notice the time does not change based on how fast I'm firing this. In fact, a great video for you to watch, go look up bullet fired versus bullet dropped. That's the title of it. Bullet fired versus bullet dropped. It was done by Mythbusters, and they say like, hey, it doesn't matter, even if it's being fired out of a gun, the time it takes for it to hit the ground, if it's shot horizontally, is the same as just dropping the bullet. Now in the next problem, we're going to see something launched at an angle. An angle changes that. If we kick this thing going upwards, now it will be in the air longer than just dropping it because you're giving it an initial vertical velocity.